This is section 13.3, part B. We just noted, or we just figured out, that when we integrate in polar coordinates, we're going to have to do our dA as an r dr d theta, and we're ready to do a couple of examples. So in example 1, we'd like to find the double integral over the region shown, and I probably should have shaded this in, so let me do that right now. I'm just looking at this piece here. That's r. And I want to integrate the function xy dA. Now, as I look at that, to set that up in rectangular coordinates would kind of be a pain, because no matter whether I did vertical or horizontal rectangles, they wouldn't be consistent, right? Sometimes a vertical rectangle would be from this circle to that one, other times it would be from the x-axis to the circle, and similarly if I went the other way. This is actually much easier in polar coordinates. In polar coordinates, I like to draw what I call a radial spoke. Starting from the origin, I'm just going to draw a ray that comes out. And I'm going to notice that I enter my region here at a radius of 1, and I exit my region here at a radius of 3. And that's consistent. No matter where I drew that spoke, I would have the same entry point and the same exit point. So that's going to make for nice limits of integration in polar coordinates. Let's go ahead and set that up right now. I'll have my double integral. Since we've decided to go with polar, my x is r cosine theta times the y, which is r sine theta, times the dA, which we just said was r dr d theta. The radius goes from an r equals 1 to an r equals 3, the entry and exit points that we were just talking about. And then the theta values, we start here at theta equals 0, and then we imagine sweeping out this region, so we stop here at theta equals pi halves. So our thetas will go from 0 to pi halves. And I guess I didn't really need to put the r equals and the theta equals there, but just for clarity, this first time I did. All right, well, let's go ahead and evaluate that integral. Simplifying the integrand, I have r cubed cos theta sine theta dr d theta. And notice this time I was integrating over a polar rectangle. My r values are constant and my theta values are constant. So if I wanted to rearrange the order of integration, I could do that very easily just by flipping them. But in this case, I don't think I want to. It's much easier for me to do the r integral by hand and let the calculator deal with the thetas. So I'm going to do it in the order that it's written. So let's see. Integrating would give me a 1/4, which I'll pull out here, r to the 4th, cos theta sine theta. And that's evaluated from r equals 1 to r equals 3. Plugging in the r equals 3 would give me 81 cos theta sine theta, minus plugging in the 1 is just going to give me 1 cos theta sine theta. And let's see here, 81 minus 1 would be 80. I'm going to pull the 80 out here. And then I just have cos theta sine theta d theta, which of course I can let the calculator do. And I actually did some of these integrals ahead of time for us this time, so we didn't have to keep pausing and didn't have to make you watch me punch buttons on my calculator all the time. When I did all of that, I got 10. That was including the multiplication by the 80 and the multiplication by a fourth. It's all in there. All right, let's try some more of these. In example 2, we're given an integral, again, in rectangular coordinates, and the limits of integration are already there. I didn't show you the region, instead I'm sort of describing it by giving you the limits of integration. The first thing I'm going to notice here is that I'm not real excited about the idea of integrating this by hand right now. I don't want to do either the dy or the dx, because either way, when I let u be what's in that exponent, I'm going to end up with either a 2x dx or a 2y dy, and I don't have either an x or a y down here to make that work. Therefore, I think I'll be much better off if I can go to polar coordinates, and I can replace that x squared plus y squared with an r squared. So let's start by doing that much. I will have e to the r squared over 2. And I know that instead of the dy dx, which is the dA, as soon as I go to polar coordinates, that has to become r dr d theta. I'm already happier, because now when I let u be my exponent here, the derivative 2r divided by 2 is just r. I got the r right there. So I'm actually going to be fine when I get to the point of actually doing this integral. But I do need to figure out my limits of integration. Let's think about what the limits of integration describe to us in terms of the region. The first limits of integration on the inside were the y's. So y goes from y equals 0 to y equals the square root of 1 minus x squared. For x, we go from x equals negative 1 to x equals positive 1. That's actually just the top half of a circle of radius 1. Right? If you think about that one for just a moment, you'd have y squared equals 1 minus x squared. If you bring the x squared over, x squared plus y squared equals 1, which is a circle of radius 1. But I only had the positive square root, so all the y's are positive. It's the top half of the circle. X goes from negative 1 to 1, so I have the whole top half. And there's my region R. All right, to get my limits of integration, once again, I'm going to draw a radial spoke, starting from the origin, going out. And I begin at r equals 0. I'm already in the region this time. So I'm going to start at 0, and I exit on this circle. Now what's the equation of that circle in polar coordinates? Well, since it was x squared plus y squared equals 1, that would also be r squared equals 1, or just r equals 1. And so I go from 0 to 1 as my r limits of integration. For theta, we start here at theta equals 0, and imagine that sweeping all the way around, we end here at theta equals pi. All right, we've got our integral set up. Now, as I mentioned before, this would not be difficult to do if I did want to do the dr first, but let's think about this for a moment. Wouldn't it be even easier to integrate the d theta first? Because all of this is constant with respect to theta. So I think I'm going to go ahead and take advantage of the fact that I have a polar rectangle. All my limits of integration are constants, meaning if I want to reverse my order of integration, I can do that. Make that d theta dr. Oops, only one d needed there. And then my limits of integration also are reversed. Again, I can do that because there were no variables in the limits of integration. All right, this is really nice because integrating a constant, I just get that constant times theta as theta goes from 0 to pi. Multiplying by the, plugging in the pi, I just get a pi here. And of course, plugging in the 0 will give me 0. And so I now have an integral, which again isn't difficult to do by hand, but I can do it even more quickly on the calculator. And when I did this one, I ended up with 2.038. So, something to keep in mind. When we're that lucky, when our integrand only depends on r, notice what happened. We're always going to get that integrand times theta. We're going to plug in the limits of integration, which is essentially going to pull down that pi, or whatever your upper limit is. If I had something that was non-zero here, I of course would have had to have subtracted that as well. We'll begin to use that shortcut quite a bit earlier, and I'll show you exactly how that works in the next problem. All right, this next one is a volume problem. We'd like to find the volume above the xy plane and below the surface. Z equals 20 over 1 plus x squared plus y squared minus 2. I'm already thinking polar coordinates because of that x squared plus y squared. That's usually a good signal that polar coordinates are going to work well. But in order to actually see what's going on here, let's take a quick look at this through, I think I'm going to go ahead and use GeoGebra this time. And I won't do all of the problems in both Maple and GeoGebra. I'll alternate just so you get a reminder of how to use both. So here's my graph in GeoGebra. I've gone ahead and just typed it in as z equals the 20 over 1 plus x squared plus y squared minus 2. And you can see we've got a decent graph here, but it looks like the top's being cut off. If I would like to see more of that, I can zoom out. It's actually going to have to get pretty tall this time before I see what happens. There, you can kind of see up here between 15 and 20, there's sort of a peak. And that makes sense. When x and y are both 0, I'd have 20 minus 2, or 18. Should be that peak right above the origin. So I can see what my graph looks like. I can also see the intersection in the xy plane looks like it's going to be a circle here. So I'm going to take that back and I'm going to sketch that, and then we'll talk a bit more about what this tells us. So it looked like in the xy plane I had a circular intersection, and then this thing went up to this peak right above the origin. All right. So a couple of things. First of all, I probably do want to do this in polar coordinates. So my surface here, I'm going to think of as z equals 20 over 1 plus r squared minus 2. And so when I go to find the volume, I'm going to take the double integral of that height function. The height is really just the z value, 20 over 1 plus r squared minus 2. Technically, I have to take the upper minus the lower, the top z minus the bottom, but I'm going above the xy plane, so the bottom here is just z equals 0. So I could put a minus 0 here, but there's no real need to write that, so I won't. The dA in polar coordinates is r dr d theta. All right, what about the limits of integration? Well, my region has to be the region in the xy plane. So my region is that circle right down there in the xy plane. If I just really quickly redraw that, it's going to look like that. just by looking at that much of it, I already know the theta is going to have to go all the way around from 0 to 2 pi. So I could put those limits of integration in immediately. But I need to know the radius of the circle, because when I draw a radial spoke, I start right in the middle here at r equals 0, but I need to know when I'm going to leave the region, what that outer r value is. In order to figure that out, I'm going to find the intersection of my surface with my xy plane. In other words, I'm just going to set these z's equal to one another. A little bit of algebra here. I'm going to multiply both sides by the 1 plus r squared, which will cancel it out on the left. And it looks like I'm going to get 18 is 2r squared. R squared is 9, or r is 3. So this circle would have equation r equals 3. That actually describes the entire circle. And I know I'm going all the way around because we already went from 0 to 2 pi on our limits of integration. All right, we're ready to do the integral. Now, before we jump right in, this is where I'm going to use that shortcut again. Notice all my limits of integration are constants, so I can integrate in either order, dr d theta or d theta dr. And since all of this only depends on r, this integrand is constant with respect to theta. That's a big advantage to me, because now what I can do is just think, well, if I do the theta integral first, all that's going to happen is I'll get a times theta here. I'll plug in the 2 pi. The 0 won't do anything. And I'm just going to end up getting a multiplier of 2 pi on that. So I'm literally going to say, I just did that integral. It gives me a 2 pi. So how nice is that, right? It saves us a lot of time. That gets me down to an integral that I can do on the calculator. And in fact, I did that one. Let's see, on this one I ended up with 88.127. And again, that included already multiplying in the 2 pi. By the way, hopefully I've punched the numbers into my calculator correctly when I did this, but if you get a different value, let me know sometime when we have a class meeting, and I'll be more than happy to double check that if you're getting a different value than I am. It's possible I hit a wrong key, so don't spend too much time worrying about that at this point. All right, we will pause there and come back for a few more problems.